Today we study kinetic theory of ideal gas, and perhaps everybody knows the equation for ideal gas already. That is PV equals mkBT. Today we derive this equation, assuming that uh, ideal gas consists of structureless molecules, point-like molecules, and it is in thermal equilibrium at temperature T, and this one gives the explicit definition of the temperature, including the normalization factor called Boltzmann constant Kb. And this equation is true only if this number of molecules becomes infinite. And infinite means it must be at least of order Avogadro's number, something like that. That is not exact the, the exact definition of large number, but it gives some feeling to us what a large number is. And this equation is in contrast to the equation of motion for a single particle. It is average value. That means as the number of particles increases to a very, very large number, average value at equilibrium state gives a very interesting correlation. So after finishing this class, we'll become to know what KBT means. Until now, when we from the stage when we begin with the thermal physics, we repeatedly talked about the average kinetic energy of molecules inside a gas, and that is the actual definition, exact definition for KBT really appears in here. If we consider kinematic variable for gas, they are defined not for a single molecule, but for many, many molecules. First of all, pressure. Pressure is for liquid dynamics. We fluid dynamics, the force divided by area. And for example, weight is on top of a piston, that is piston of a cylindrical container. It pressed down with its own weight mg on the piston of a surface area, cross-sectional surface area A, then the pressure is defined in such a way. But if in this case we know what the force is exactly, however, the they are in equilibrium with the gas pressure, and that means if this total system is in equilibrium, from outside we can see there is a certain force downward, but it indicates that the equilibrium indicates that there exists another force pressing up the weight by as a result the resultant force, that force on the whole system vanishes. Uh, this indicates that molecules give the pressure upward. How? There's a plate, this is a piston, and molecules are going up, and it collides with the piston wall, and that returns. During this time, In addition, if we consider the volume, for example, if we have a single molecule, do you know what volume is? It is not well defined. For example, its own size is a very, very tiny, too small to describe. But if there is a big container, we can say it it container with a cubic container with every side L, then the volume can be understood to be LQ. But the actual size of this molecule is very tiny, so uh, it is not really definite. I'm not sure what the volume of this single molecule is. However, if there are many molecules in this container, even though there are empty space, the more or less we can we can see how these objects are distributed, and only if this number of molecules becomes very large, we can more or less define the volume of this molecules occupied by the molecules. If we add more air molecules inside, then we will see the pressure is increasing because the number of molecules in because of the number of molecules has been increased. Uh, the period, the frequency of hitting the wall by the molecules will increase. That results in the increase of the pressure. That is due to the additive nature of forces. Among these all macroscopic scale variable, pressure, volume, area, and total mass, the temperature has a special feature in comparison with these variables. Temperature, we will find that the temperature is closely related to the average kinetic energy of the molecules. So that is the average. It is not additive sum. After making the sum of total net sum, we divide the number by the total number of particles. So temperature, except for temperature, everything else seems to be additive, but temperature is averaged out. In the derivation of the kinetic theory of ideal gas, that is PV equals NKBT, we will derive the relation from a single particle and multiply by the n particles and actually average over the n particles. So we need to know the relationship between the macroscopic variables P, V, and T, and the microscopic variable that corresponds. This macroscopic variable is also appears the total mass of the gas. Microscopic variable such as kinetic energy 1/2 mv squared for each particle. And to describe this kinetic energy, we need to know the mass of a single molecule and velocity of a single molecule and velocity squared and so on. So we go back and forth between the macroscopic variable and microscopic variable. And at the end of the day, we'll find uh, the equation of motion for ideal gas. Let us consider motion of a single molecule inside a cube.
Uh, Before we begin with our analysis, we assume that, as I told you, single molecule, if you consider a single molecule, it is volume, pressure, and the macroscopic kinematic variables for thermodynamics are not well defined. And therefore, we assume this is the volume of the ideal gas consisting of a single molecule. But as you can see, the pressure is not well defined because pressure is produced by the momentum transfer of a molecule when it collides with the wall, and it is not continuous. The force application is not continuous but discrete. For a very short time, when it touches the wall, it transmits momentum. However, after that, until it returns to the same position, it is free. So the pressure is defined only if we average over the many, many periods. I mean, if I measure the pressure on the wall during the time, in a very short time, when it does not reach the wall, then pressure must be zero. So that's the reason why I told you that a single molecule or a few molecule system is not adequate to describe a gas system. That is valid only if the number of particles increases. Because there is only a single particle in this case, in order to define the pressure of the molecule on the wall, we need to measure the pressure for a very, very long time, so that even though there is only a single molecule, it allows the motion, repeated motion, so that for a very long time, this molecule applies momentum transfer to the wall, sigma of delta P for each collision, and sum over the collision, and let the collision number of collision to be infinity, something like that. Then we can reach some point. Okay, so let us first define the size of the box that is a cube of each side L. A molecule is traveling inside the cube, and when it is in the middle, inside the cube, then the momentum and the velocity is constant. These are the x, y, z component of the three momentum of the single molecule. When it touches the wall, there is a reflection, and in general, collision can be either elastic or inelastic. Sometimes it is completely inelastic. The molecule may stick to the wall, but we do not allow any inelasticity. So we assume that every collision of a single molecule to the wall is perfectly elastic. So energy conservation, that the energy is not transferred to the wall, and the internal energy of the wall is fixed. So we don't care about this, and we only consider the internal kinetic energy. That is just kinetic energy of explicit kinetic energy of a single particle of the system. In addition, if we ignore the mass of the world, the mass of the molecule should be very large. So every time it collides with the wall, this wall may vibrate. So we do not allow, in order not to allow that kind of situation, we assume that the wall is infinitely heavy. In that case, the center of mass is just the center of the cube, and the mass of the molecule can be negligible. So in the center of mass frame, we can consider the total linear momentum is 0, and however the total in comparison with the total kinetic energy is the kinetic energy of the particle. Anyway, the total linear momentum of this single molecule system is not conserved actually, because every time it hits the wall, it reflects. So momentum at some stage and after the collision, momentum is flipped. And actually that momentum is transferred to the whole system. So the same amount of momentum is transferred, but it is very heavy, so box doesn't move. That's the situation. Okay. To simplify our analysis, we make a projection onto a single axis, each for x-axis, y-axis, and z-axis. If we choose I equals 1, it is a projection onto the x-axis motion. If we consider the motion along the x-axis only, then the velocity x1 dot involves. And it repeats. Suppose that we have x-axis along here, y and z-axis. If we consider the motion of along the x-axis, it repeats the motion with the x1 dot positive value, and then after hitting the wall, it reflects with negative value. And then if it hits the wall on x equals 0 and x equals L, it repeats the motion with the velocity x1 dot and minus x1 dot forever. So when after it hits the wall at t equals 0, in order to return to the same point, it travels with the distance 2L. This side is L, and round trip is 2L. The distance of round trip is 2L. Okay. And we have 2L and speed. So this is the period of hitting a single wall that is perpendicular to the x-axis, 2L over xi dot. So this is for I equals 1, 2, and 3 separately. Let us compute the force applied to a single word in here. So every period, it hits this wall with the initial momentum x1 dot and final momentum, initial velocity, final velocity with minus x1 dot. And there is a wall, and this is x-axis. And linear momentum is the product with the mass. And this is the initial P1I and P1F, final and initial. Change in momentum is along the x-axis. It's a P1F minus a P1 initial. That is Final is a minus x1 dot m. Initial is mx1, so minus mx1 dot. So minus 2 mx1 dot is the momentum transfer to this molecule. Because of action and reaction applies, the Newton's third law states that the momentum transfer to this wall at x equals L is opposite sign, if equal amount and opposite sign. Okay? So momentum transfer, delta P, along the x-axis, the I-axis, is this amount. And for every this period. So momentum transfer divided by period should be average force applied to this wall if we measure this pressure or force for a very, very long time. In that case, the inverse of this period, delta t is just the ti, and inverse is this. 2 cancels. What I obtain is a mass times the velocity squared along the x-axis, I-axis, divided by length. Once I know the force applied to the wall, I can measure the pressure on that wall. And pressure is the force divided by area, and the cross-sectional area of this wall is L squared. So if I divide this quantity by L squared, we have denominator L cubed, that is the volume of the cube. Therefore, the pressure on the wall at x equals L is mx dot squared. This is along the I-axis. This is true for the other wall at x equals 0. That is perpendicular to the x-axis. In summary, if there is momentum, velocity, it is decomposed into 3 Cartesian components, x1 dot, x2 dot, and x3 dot. In that case, in perfect elastic collision with the walls, it does not change the magnitude of this velocity. The speed along the x-axis, y-axis, and z-axis are invariant, but the direction is flipped as whenever it collides with the wall. We have 3 curves. The red curve, that is just a straight line with opposite slope. As soon as it touches the wall, it flips the direction. So it is the magnitude, the slope is conserved, except that the sign of the slope changes in every collision with the wall. And we have a green that indicates the trajectory along the y-axis, and the third one shows the z component. So in such a manner, every single wall of a cube accepts the pressure of this amount. If we consider only a single particle, this mx1 dot squared over v, mx2 dot squared over v, mx3 dot squared over v, that are all invariant. We have assumed that this wall is flat, so we cannot change the magnitude. So speed is always the same. So it is the distribution for x component, y component, z component. If it is fixed at some point, we cannot vary anymore. Okay, but actually it is a little bit unrealistic. In fact, when we measure the pressure on every word, they are the same. They are the same. We do not have a way to distinguish the pressures on 6 words. In fact, when we increase the number of molecules, this is an extremely ideal case, only a single molecule case. So we are almost ready to write down the equation for ideal gas, but let me introduce the central limit theorem to increase the number of molecules inside a box from a single molecule to n molecule, where n is an extremely large number of order Avogadro's number, that is 10 to the 23 or more or larger. Tossing n coins. If we have a coin, we toss a coin with a front side and back side, and if we toss, then it appears front or back. And let me write down the probability of finding front side to be 1/2, then the probability of finding back side of 1/2. And the P plus Q, the probability of these two, is 1. Suppose that we throw this coin by n times, and let us find out the distribution of a probability distribution for finding R. R is the number of front sides among n throws. This is the actual distribution calculated with the additional factor, this one. As you know, this probability distribution comes from the expansion of p plus q to the nth power. Binomial expansion gives it as let me write it as k. K equals 0 to n. We have nth row, and front is k, and back is n minus k. And probability of finding k fronts and n minus k back sides, this is the exact identity. And we have additional normalization factor square root of n to show the maximum value to be the same. You know, this, as the number of throws increases, the normalization should be fixed. That is to correct the normalization to show the distribution. The sum of the multiplicity is 2 to the 2n, so it increases very large as n goes to infinity. So we divide this by, we multiply by the square root of n, then the maximum value is frozen or somewhere else. And then later in the, not this lecture, but the subsequent lectures, let me derive the exact number for this normalization. And the central limit theorem is nothing but this. As you can see, the distribution of a probability distribution of finding the front side varies. However, for a small n, such as 10 is a small in this case, and if we increase the number of throw, then the width decreases, and 1000 is very narrow in comparison with a a smaller number of trials. In addition, every distribution has an average at the central value that is 1/2. This is a central limit theorem. Average is always at the center and actually determined by this P, and the width of the distribution becomes narrow as we increase the number of trials. This one shows if we increase the number of molecules, then calculation of the pressure, right now we have a specific number that are invariant for XYZ axis for the pressure. If we increase the number of molecules very large, not this small number, but to the 10 to the 23rd or much larger, then the average value will be sharply peaked at the central value, and the pressure becomes well defined, very, very well defined. So let us go ahead with this knowledge. This one shows that the distribution is saturated at the center. I have restricted the region for the nearest region at 1/2. You fix the window, increase the number of trials, and when the number is rather small, I don't really see the big tendency, but as we increase, there is over 1000, 1024, and if we increase it further, it is absolutely 100% concentrated in the central window. This is a central limit theorem. So let us increase the number of molecules of order Avogadro's number. All right. First, look at the average value of velocity along the XYZ axis. Now, we can make use of our basic postulates. You pick up a single molecule. You don't know how it moves. There's a random distribution of many particles. You are not so sure about the exact value for the velocity for a single one, but in total, there are so many things. First of all, is it going to the right or going to the left along the x-axis? I do not know what it is. However, if we increase the number of particles, if you pick one of them, the probability of finding the one that is moving on to the right and left, it should be 1/2. Because the nature does not have a preference over left and right. In a similar manner, the distribution of the velocity, it should be there should be some average value and just some distribution. Here is a x dot 1 is a positive, and here x1 dot is negative, and there should be left to right symmetry in the space. I don't see any asymmetry of the space because the space is isotropic, left to right symmetry, and the XYZ axis symmetry, that will lead the fact the average value of the velocity distribution must be 0. And I don't see any difference among XYZ axis. So that must be true in every component, Cartesian component of the velocity. So this is a kind of postulate, but it is not mathematically given, but our experience sees there is no way to distinguish. If we measure many times and for many molecules, this one happens. If you have a single one, but you can measure the velocity so many times, then the similar result will appear. So anyway, average value of the velocity along any direction must be 0. Here, the average value should be the sum of all of the molecules velocity and divided by the number of molecules. In a similar manner, I can compute the velocity squared along the xyz axis. And velocity squared is x velocity squared and the y component squared and z component squared. This one is x1 dot squared, x2 dot squared, and x3 dot squared. Here too, I don't see any difference among xyz components. There should be no difference at all in the Euclidean three-dimensional Euclidean space. So what I claim is that this is non-zero. First of all, even though there is a symmetry, the left-right symmetry cancels in the linear expression, that is odd function, but this is an even function. If I square this, it's a momentum squared, the velocity squared, that is positive definitely. So it should not be zeros. I don't know the answer, but it should not be zero, as far as I know. And their XYZ components must be the same, and that means that each of them should be 1/3 of their sum. And their sum is the velocity squared. This is called the equipartition theorem. I don't have any way to distinguish XYZ directions. Equipartition theorem. Now we define temperature. We have reached the point these three values are identical when we average over the large number of molecules. And this is twice the kinetic energy along a single axis. So we have 1/2 m x1 dot squared, x2 dot squared, and x3 dot squared. This is the kinetic energy of a single molecule, and this is the average over the n molecules. So this is the kinetic energy. But this one shows that only a single part n doubled. So mx1 squared average is the double of the kinetic energy along the x-axis. And we define, because they are all equal, we define this one to be kBT. That's it. So this is the energy. Energy has a scaling factor kB that is called the Boltzmann constant. So temperature is defined in such a way. This one is energy. kBT is the energy, twice the energy, kinetic energy along a single Cartesian axis. So if I multiply 1/2, kinetic energy along the single Cartesian axis is 1/2 kBT. If our gas is in one dimension only, this is the kinetic energy. If the gas is moving around the two dimension, then we have x component and y component. So in that case, we have 1/2 kBT multiplied by 2. In fact, we have three-dimensional Euclidean space. Therefore, our average kinetic energy per molecule is 1/2 m x vector squared, average. That is 1/2 m x1 dot squared, x2 dot squared, and x3 dot squared average. So it is 3/2 m x1 dot squared average. Okay, this is kBT. So 3/2 kBT is the average kinetic energy of a single molecule moving around in the three-dimensional Euclidean space. Now we have a pressure along on a single wall that is perpendicular to a certain Cartesian axis. It's perpendicular, and we average over n very large molecules. Average. This is the sum. Because if there is a single force and double force, the force adds up. So pressure due to the n molecule should be summed. So the sum is the average multiplied by the number of molecules. Okay? So sum of pressure due to the n molecules is computed as this one. And what is this? This one is kBt. So this is pressure. Pressure equals n kBt over volume. That's the ideal gas equation. Ideal gas equation, pressure is number of molecules multiplied kBt. What's that? mxi dot squared average for a I equals a single Cartesian component. That's it. That's ideal gas equation. Avogadro's number is a very large number, and of approximately that order or larger, this equation becomes valid, and the system should be in thermal equilibrium in temperature T. That means now the thermal equilibrium is the limit where n goes to infinity, and in that case a central limit theorem dominates. So every value of the molecules, the distribution is concentrated at the very sharp peak, has a very sharp peak at the center. And this one means whenever you measure the pressure, volume, or temperature, they are well defined because of this limit. What Avogadro's number in practical use? We have a mass number. For example, consider hydrogen atom, hydrogen molecule. Hydrogen molecule is just a hydrogen two hydrogen atom. If we neglect the binding energy contribution, the mass of the two is identical to each other. So the mass number for proton and neutron, they are 1. So H has a mass number A, atomic number. Atomic number and mass number are the same for hydrogen. They are just 1. There is no neutron in here. Both of them are 1. So we have 1, but you usually measure in some physical units. The gas is very light. It's good to make use of gram instead of kilogram. 1 kilogram gas is a very large amount. And 1 gram. We have a mass number is 1. What is the number of molecules to have it 1 gram. That is Avogadro's number. So the mass number we do not use the unit for mass, just a pure number. If I want to restore the physical unit as a gram, what I need is Avogadro's number. So in case H2 hydrogen molecule, 1 mole of a hydrogen molecule, then it is a 2 gram. So Avogadro's number, the molecules of Avogadro's number is called 1 mole molecule. But in this case, atom, 1 mole atom, hydrogen atom is 1 gram. 1 more hydrogen molecule is 2 moles of hydrogen atom. So that's the reason why it is 2 grams. In a very large scale, it's useful to make use of Avogadro's number. So we divide Avogadro's number and multiply. It is just that we have multiplied just the 1. And this becomes the number of moles, and this becomes gas constant. We notice there is a huge number in the Avogadro's number. This factor is cancelled by the very tiny number in the Boltzmann constant. So in practice, for example, in chemistry, it is useful to use a gas constant that is product of Avogadro's number and Boltzmann constant. In an isothermal process, in the previous class, we just copied the result, but now we have derived the ideal gas equation, the PV equals to NKBT. So now we understand why the overall factor is NKBT for the constant temperature process. Next, we consider root mean square speed. We remember every component of V squared, Cartesian component V squared average should be the same, and that is 1/3 of the velocity squared, through which this is the fundamental basis of deriving equipartition theorem. And equipartition theorem, in combination of equipartition theorem, we were able to define the temperature, absolute temperature of a molecule. As a result, velocity squared along each Cartesian axis, average is kBt over mass of a molecule. We define root mean square speed, that is square root of average value of the velocity squared. Okay, square root of average, that's a mean, squared velocity, that is RMS, root mean squared speed. And as we know, this one squared is a squared velocity average, and these consist of the 3 components. For each component, every component should be the same. So we just pull out, for example, x-axis component, and we have to multiply factor of 3. So if I take the square root of everything, then we end up with square root of 3 kBt over m. This is the reason why this kBt is defined along a single Cartesian direction. Because we are living in the 3-dimensional Euclidean space, we have a factor of 3 inside the square root. Again, we can multiply a very large number, numerator and denominator. This one gives a gas constant, and Avogadro's number is multiplied, then this This is the molar mass. That's the mass of the gas sample with 1 mole molecules. Graham's law shows that the RMS speed is proportional to the square root of temperature, and when the temperature is fixed, this is constant, and velocity becomes is proportional, anti-proportional, reciprocal to the square root of mass. So because of this, this is a light and this is a heavy, and it used to be occupying the same amount of space, but as time goes on, they diffuse, they are flying because they have a certain velocity, average velocity. That is represented by RMS value, but the heavy one does not propagate too much, but lighter one propagates very much. It is the ratio is exactly the square root of mass ratio. Because of this, we can make a very simple estimate how we are surviving on Earth. We learned that the RMS value can be computed in such a manner. So RMS of the air molecules for nitrogen and oxygen, they are of order several hundred meters per second. It is very fast. We can guess that it may be possible, if it is very large, then it can escape from Earth's gravitational field. Let's check. We learned that escape velocity of any particle that can escape from the Earth's gravity is 11 kilometers per second. It's very, very fast. This one is fast, but is still much smaller than the 11 kilometers per second. That's the reason why the air molecules are trapped on the surface, around the surface of the Earth, and we can breathe. Next, we consider self-test. This is for majorly concerned about the Gaussian distribution. Gaussian distribution. At the end of last class, we evaluated this Gaussian integral to be square root of pi. And actually, this distribution is a symmetric. There is a symmetry about y-axis. Y equals e to the minus x squared. The left to right symmetry is an even function. But we can modify it by subtracting some amount from x and divide by 2 sigma squared. We'd like to see what this means and what this sigma squared means. For example, if we want to translate this one as a probability distribution, any discrete probability sum should be 1. In the continuum limit, this is a function, so it is a continuum limit of a kind of distribution. This distribution has a normalization. When it is integrated over the whole space, then it should be 1. So I'd like to determine the coefficient c. This c is not the speed of light, it is just a normalization factor. Okay, we know how to evaluate the Gaussian integral. So first we make a translation. Any integral from minus infinity to infinity that is integrable, that means and tells the infinity plus infinity and minus infinity, they are integrable, and the functional value must be exactly 0. If it does not approach 0, the definite integral is not defined, it diverges. So after translation, so translation and invariance holds for this one. So I can change the variable by this amount, and I can remove that one. And then we can change the variable. This one can be expressed in terms of this Gaussian integral that we know that is square root of a pi. So using this relation, I multiply 2 square roots 2 sigma, square root to 2 sigma in the denominator. In the numerator, we have a square root to 2 sigma. Okay. In that case, this one is Gaussian integral of square root of pi. Finally, I can determine the normalization factor C is 1 over square root of 2 pi sigma squared. So I have found that this is the normalization factor is this. That satisfies this normalization condition for any probability distribution. Now let us look at this value and this value. What are they stand for? Why don't we just evaluate the average value? Average value is x px integral. This is one when the probability density is given like that, we can obtain the average value. Then average value can be evaluated by translation. We have this addition plus c in here, and then we find this is an odd function, integrate it over the symmetric left-right symmetric region. So this one disappears and only this contribution survives. And what is this? We find that this one is exactly the average value. Therefore, in the distribution, probability distribution, this one represents the average value of this distribution. We say it is a normal distribution. As the last stage, we want to know what this denominator factor is. We can compute the variance of the distribution for the probability distribution. Usually variance is computed in this way, average value of the square, and we can compute separately. Plus, and this is as it is, and this is number. This average is minus x average squared, and this is plus average square. So as a result, is a square subtracted by wait a second. This is right. Average square. Average square. Average square. Okay, this is a way to compute the variance, and you will find we have studied the gamma function, Euler's gamma function, and we have reached the result for this. Finally, the variance is identified to be sigma. So this is called the normal distribution with the average value and variance sigma square. The standard deviation of is the square root of this, and this width becomes that is the width. Next, we consider binomial distribution, and in the next classes, we study the central limit theorem. We will try to understand what the central limit theorem it is, and it's good to follow this calculation to find out the average value of binomial distribution is this. perhaps I believe you learned in high school. And variance is NPQ, where P and Q are the probability of two cases. So the front side or back side, their sum is 1. So the answer is average is NP and variance is NPQ. When P and Q are both 1/2, then the average value will be 1/2 of n, and the variance will be n over 4, the 1/4 of n, and standard deviation will be square root n over 2. That's it for today. Thank you.